presentation of our final project, Better Anchors, Better Text, Rethinking Anchor Selection in Anchor Diffusion Language Models. My name is Tim Liu, and today I'm working with my teammates Junhao Zhu and Yuyang Lin. To begin with, let's look at the problem we're trying to solve. Most traditional language models are autoregressive. This means they generate text from left to right, one set token at a time. This approach is very powerful, but it also has some limitations. First, generation is sequential, so it is hard to fully parallelize. The model has to generate the first token before the second token, and so on. Second, early positions do not have access to the future context. When the model generates the beginning of the sentence, it has not generated the later part yet, so it does not have a fully global view of the sequence. Diffusion language models provide a different direction. Instead of generating text strictly from left to right, they gradually denoise the sequence. This means the model can update many positions at once and use more global context during generation. Our project focuses on ADLM, Anchor Diffusion Language Model. The key idea of it is that not all tokens are equally important. Some tokens carry more semantic information than others. So ADLM introduces anchor tokens. These anchors are selected tokens that are more important than other tokens. Once these important tokens are reconstructed, they can guide the generation of the remaining context. However, the original ADLM selects anchor words using a simply frequency-based heuristic. In other words, real tokens are more important than the words with high frequency. The problem is that the real words are not always more important than the word with high frequency. So our contribution is to rethink anchor selection. We propose a modular score and threshold framework where each token receives an important score and anchors are selected based on that score. Now I will briefly introduce the related work on diffusion language models field. D3PM, SEDD, MDLM are three major methods to complete the diffusion task on context right now, but they all have similar limitations. They do not care about the importance of one token at all. Instead of applying diffusion directly over tokens, LD for LG first compress the token into latent space and then perform diffusion there, and then decode it back to the content to the text. This can make the diffusion process smoother, but it also introduces a more complex pipeline and usually requires more training time. ADLM is the baseline of our project, as we just discussed. So our project is also related to token importance methods. One simple approach is frequency-based selection. These methods assume that real words are more informative. They are easy to compute and do not require model training. However, they ignore context. Another approach is perturbation-based attribution. The basic idea is to remove a token and measure how much the model output changes. If removing a token causes a large change, then the token may be important. This method is more directly connected to model behavior, but it can depends on the task too much. For example, important tokens in translation tasks may not be important in a Q&A task. The third approach is semantic similarity, which is the direction we use in our project. Specifically, we use keywords. Keywords embeds both the whole document and the candidate words using a sentence transformer. Then it ranks candidate words by their cosine similarity to the document embedding.
Then I'll move to the methodology of our framework. So first, we have designed a score and threshold framework to ensure that all of our anchor words are thresholded and have an individual score. Since the anchor loss encourages earlier reconstruction of designated anchor positions during denoising, we're hoping that our framework is able to provide a set of words that is available. First, we'll intake input sequence X. Then, for each position, we will utilize a scoring function which provides a score between 0 and 1 individually. After that, we will have a percentile thresholding to make sure that a certain group belongs to the input sequence will be chosen. And finally, all the selected tokens will count towards anchor loss, while others will not. The second design is our keyword scoring pipeline, a little bit different from the standard keyword scoring. First, we will conduct a candidate extraction, which extracts each unique words after stop word removal to introduce a candidate set. And second, we will have an embedding module, which utilize a frozen sentence transformer to produce sequence level and also the per candidate embedding. And third, we will do the scoring. We will calculate the cosine similarity between each candidate and the whole document embedding with all the stop words get a score 0. And finally, we will normalize a line to make sure that each word in between the sentence will have a score between the intervals 0 to 1. A key advantage of our scoring pipeline is that we enables offline pre-computation so that scores only depend on the words and the sentence themselves. We can compute them once and save them and reuse them multiple times across different percentile settings.
To evaluate our framework, we computed metrics over 1,000 unconditionally generated samples. For quality, we measured generated perplexity using a frozen GPT-2 large to assess fluency and naturalness. We also used MOV to measure the distributional gap between generated and reference text. For diversity, we tracked self-glue 3 to measure intersample diversity, and unigram entropy to capture lexical diversity and vocabulary breadth. Our experimental setup utilized the Open web text dataset with a text length of 512 tokens. We trained a small DIT configuration and a dual backbone totaling roughly 290 million parameters. Training ran for 300,000 steps onto 800 GPUs. Under matched compute, we tested 3 main anchor configurations. A non-anchor baseline where the anchor loss was disabled. A frequency configuration using the original ADRM heuristic. Our keywords configuration with semantic scoring, swapping the anchor ratio across 10%, 20%, and 30%.
And then move to our main results. One outcome that we have is that anchor selection matters. So in the chart below shows that results from different methods, including no anchor baseline, frequency-based selection, and 3 different anchor ratios designed for keyword. The first result that we would like to conclude is that semantic anchors improve the generation quality. It decreases perplexity by 6.5% and also increased MOV score by 12.2%, indicating a strong improvement in generation quality. And second, frequency-based anchors might degrade quality in comparison to unanchored baseline. Third, diversity matrix unchanged across all conflicts, indicating the outcomes that we have in improving generation quality does not come with a cost of the generating diversity. And second is the effect of anchor ratio is non-monotone. From the chart shown on the right, both metrics trace a clear V shape, which is the generated PPL and the MOV. Only when the ratio set to 0.2 improves over baseline. That is to say that the anchor ratio must have a sweet spot in between 10% and 30%. Either 10% is carrying too few information, or 30% carries too much information that might confuse the generation quality and also might not serve as a good guidance. Also, we would like to conduct a qualitative analysis on what gets anchored. Below is a representative passage from our training set, which is a chapter from it. As for a token with 512 tokens, frequency-based method might select over 60% of the text. So all the bold purple parts are anchor tokens selected from different methods. Frequency-based usually select some words like and, after, about, it, and many more words that does not carry informative message. While for keywords, 0.2 is a best configuration that carries the most sufficient and also proper words that carries the whole information of the selected text. Then we would like to show inference procedures without anchors. So from the video, we can see that at early stage, we usually have some arbitrary words of, some numbers, some single words like J, K, and the. And for frequency-based anchors, we would also have found a very similar pattern to generate some arbitrary words at early stages. And then it is the inference procedure with keyword anchors. At first stage, we can see words like aggressive, like earning, like it, like up, and also many more words that has actual meaning, which is something that we would like to see from better anchored guidance. Overall, we would like to conclude that anchor selection is a first-class design access in ADLM, not merely an implementation detail. That is to say, anchor selection is the main reason why ADLM has a better performance over other standard discrete diffusion design. And second, frequency-based anchor is not a universal solution. In ADLM, it claims that by training in a context window of 1024, it has a strong improvement on MOV score. However, when we compress the length to 512, it no longer works. And third, keyword anchors at a specific ratio might have a very strong improvement in generation quality without any diversity loss. And fourth, the effect is non-monotone, indicates that both what is anchored and how much is anchored both matter for this generation guidance. And for future directions, we have 3 different directions that are both important, that are all important. First is we would like to have a learned scoring function trained jointly with the diffusion model instead of a 2-stage pipeline. And second, we would like to mask anchor words in forward pass dynamically. And third, we would like to validation our idea across larger models, multilingual data, and domain-specific corpora. And that's all of our final project. And here are the reference pages. Thank you.